Okay, so in this video we're going to have a look at 5 difficult exam questions involving bounds. Now the question that's on the screen is the one that we're going to build up to. I would say this is the hardest out of all of them, but we're going to build up to that and have a look at these 5 questions. Now make sure you have a go at all these questions, so grab a piece of paper, grab a pen, make some notes, and with that being said, let's get started. Okay then, so looking at our first question. Now with all bounds we are going to be using a calculator for all these questions, so make sure you've got your calculator. And also in regards to all of these questions, it is important that you have a good understanding of bounds already, so do make sure that you check out the full lesson or the full video on bounds that I'll link in the description. Okay, so do make sure you check that out first and then maybe come back to this one, but if you're already happy with your bounds, then let's get started. Now this question says a solid metal cube has sides of length 125 millimeters, correct to 3 significant figures. It says that cube is melted down and the metal is used to make solid spheres. The volume of each sphere is to be 140 centimeter cubed, correct to the nearest 10 centimeter cubed, and it wants us to work out the greatest number of spheres that could be made from that metal. Now essentially what that means is, and let's draw a little picture here, we've got a cube and the side lengths we've been given there are 125 millimeters, correct to the nearest 3 significant figures. And this is going to be melted down, so the volume is going to be melted down, and we're going to make these cubes out, these spheres out of it. So we need to figure out how many of these spheres that we can make. Now thinking about the logics of this question, the greatest number of spheres would come if we had the largest possible cube and we made the smallest possible spheres. So what we're going to do is we're going to work out what's the biggest possible cube that we could have there, and what is the smallest possible sphere that we could make, and that's going to give us our greatest number. Now, bearing in mind that in this question already, we've had a little issue. We've got this length given to us in millimeters, and we're looking at a volume in centimeters, or centimeters cubed. So we want to keep all the units consistent. So let's first turn that 125 millimeters into centimeters. We could convert the volume into millimeters, but it's probably just easier for us to write this as 12.5 centimeters. And as with all bounds, we're going to write the inequality for that. So our error interval is going to be, and let's draw our arrows, we're going to have 12.45 as our smaller or a lower bound there, and 12.55 as our upper bound. And again, we have an equal to symbol underneath that inequality on the left. So to get our largest possible volume here, we would want to use the largest length for the cube, which is 12.55 centimeters. Now, as it's a cube, if each length is 12.55, the length, the width, and the height, we would multiply all of those together in order to get our volume. So we're going to get the largest possible volume, which is 12.55 multiplied by itself 3 times. Let's write that as 12.55 cubed. Let's work that out on the calculator. So 12.55 cubed gives us a volume here, and it's not a very nice number, but we get 1976 point, and we've got a few decimals here, 656,375. That's now in centimeters, so centimeters cubed. And there's the volume of our cube, or our upper bound for the volume of our cube. So that's the largest possible volume we could have if the lengths are that largest possible length. Now we'll have a look at the spheres. Now, it says the volume of each sphere is to be 140 centimeter cubed, and that's correct to the nearest 5. So if we write our error interval for that, we've got 140 in the middle. There we go. And that is going to be 5 above and 5 below if it's to the nearest 10. So the largest possible volume is 145, and the smallest possible volume is 135. Now, if we are going to figure out the largest amount of spheres we can make, we want to imagine that the spheres are as small as possible, so we'll use that 135. So in order to work out how many we can make, we'll take that large volume, 1976.656375, and we'll divide that by the volume, or the smallest volume of the cubes, which is 135. So straight away, let's type that in on the calculator, and we get the answer here, 14.64, and some more decimal places. I'm not going to write them all down here because we're using a real life scenario here, and we can only have a whole number of cubes. Now what we found is we can't quite make 15, but we can make 14. So we can make 14 spheres out of this cube, and that would be our final answer to finish that off. Now that question there wasn't too tricky, okay, but there was hopefully a nice reminder there in terms of what you need to do. We need to look for consistent units, we need to write the error intervals for each question, okay, we're going to get marks for that, and we need to then just think about the logic of the question. So here we're working the greatest amount, so we took our upper bound of the volume and divided it by the lower bound of the other volume to give us our greatest possible answer there. So there's our first question, definitely the easiest out of the 5, but let's have a look at our next one. Okay, so moving on to our next question. Now the question says, James wants to cover a triangular field ABC with fertilizer. Here are the measurements that James makes. Well, let's first draw a little triangle so we can visualise this. So ABC, doesn't matter how we draw it, but there we go, there is our field. So it says angle ABC is 50 degrees. Let's put that in, so ABC is over there, so that is 50 degrees, correct in the nearest degree. We've got the length BA is 225, and that's in metres, so let's write that in. 225 metres there from B to A, and B to C is 175 metres. There we go, and there's our other length. And again, that's correct to the nearest 5. It says work out the upper bound for the area of the field, and you must show your working. Now the only reason that this question is a little bit more difficult is because we've not just got bounds involved, but we've got another topic involved. And as you'll see with some of these later questions when we involve some compound measures, that's what really starts to make these questions more difficult than your standard question where you're substituting into a formula. So this one here, we actually need to know the formula ourselves, and that's because we're working out the area of a non-right angled triangle. And again, we don't have the base or the height. So we're going to use a bit of trigonometry, and we're going to use area is equal to half AB sine C. There we go. And that's our trigonometric use for working out the area of a triangle. Now we've got our lengths A and B, we've got 225 and 175, and we have our sine C or our angle C, which is 50 degrees. Now remember, obviously the triangle hasn't actually been labelled with those letters, but when we're using trigonometry we can label it as we want. So we'll call this angle C, which will make this little one little c, and then the other sides can be labelled A and B in either order. So although it's given us A, B and C around the triangle, they're not the letters that we're going to use for our formula. And again, if you're unsure about using this part of trigonometry, do check out the trigonometry playlist and have a look at working out the area of a triangle using half AB sine C. So in order to get the largest area of the field, we're going to want the largest lengths and the biggest possible angle. That's going to make the field as big as possible. So again, just like our previous question, we need to write the error intervals for all of these pieces. So we've got 50 degrees correct to the nearest degree. Now if we write that as an error interval, there we go, that's going to be 50.5 degrees as our upper bound and 49.5 degrees as our lower bound. Moving on to the length, 225 metres. Now that's correct to the nearest 5. So if it's correct to the nearest 5, we can go 2.5 above and below. So it would be 227.5 as our upper bound and 222.5 for our lower bound. And that's that second one done. Now the next one is to the nearest 5 as well. So 175. And again, we'll go 2.5 above and below. So 177.5 as our upper bound and 172.5 as our lower bound. Now, as we've already mentioned here, we're working out the upper bound for the area. So we want to have the biggest possible lengths, obviously that's going to make the area as big as possible, and again we want the biggest possible angle. From the point of view of that letter B there, that's going to widen the gap or widen the width of the field there, so we're going to want to use all those largest possible pieces for this one. The rest of it is now just plugging into the formula. So to work out the area, we'll do half times A, which we've labelled as the 225, so that would be 227.5, multiplied by the 177.5, the other length, multiplied by sine of the angle, which is the largest one, so 50.5, and we'll have a look at what answer we get for that. So typing that in, so a half times 227.5 times 177.5 times sine 50.5, and we get an answer here. Let's write this over here, 15579, so 15,579 point, and we get 5826. Now again, there we go. Now that is in meters, so that is going to be meters squared as it is an area, and there is our final answer, 15,579 579.582 metres squared. There we go. Right, so let's highlight that off as our final answer. And there's our second question. Again, not as difficult as some of these are going to get, but you had to have your formula there and think about using trigonometry. We had to draw our own little diagram and then obviously plug all the right pieces into our formula. So there we go, there's our second question. Let's have a look at our next one. Okay, so for our next question, this is where we've got some compound units getting involved, and we've got speed, distance, time for this one. So it says a train travelled along a track in 110 minutes, correct to the nearest 5 minutes, and the length of the track is 270 kilometres long, correct to the nearest 10 kilometres. Could the average speed of the train have been greater than 160 kilometres per hour? And you must show how you get your answer. So our key numbers here, we've got 110 minutes to the nearest 5 and 270 kilometres to the nearest 10. Now we know with speed is equal to distance over time. So if that's what we're going to work out, the speed, we need to get the distance and divide it by the time. Now again, we need to think logically here, because we don't want to work out all of these bounds. It says, could the average speed have been greater than 160? Or in other words, what is our upper bound of the speed, or our fastest possible speed, and does it break that 160 kilometers per hour mark? Now in order to get the biggest possible answer here, we're going to want the greatest distance and we're going to want to divide it by the smallest possible time. And bear in mind as well, before we get started, this is in minutes and our speed is in hours. So we're going to want to get that into the same units there. But let's write our bounds to start with. So for the distance, which is going to be on the top, let's get our upper and lower bound. So if 270 is the distance, and that's correct to the nearest 10, that's going to be 275 as the longest distance and 265 for our smaller distance. Now for the purpose of this, we've already said we want to have the biggest possible distance and divide it by the smallest possible time. So we're going to have 275 on the top of our calculation. And now we need to get the smallest possible time. Now let's start by writing the bound in minutes. So we've got 110 minutes. And that's correct to the nearest 5, so we're going to go 2.5 above and below. So 112.5 would be our upper bound, and 107.5 would be our lower bound there, our smallest possible time. Now that's in minutes, and we want that in hours. So in order to turn that into hours, we're going to want to divide that by 60. Okay, so divide that by 60 minutes. There we go, 60 minutes in an hour, and that's going to turn that into hours for us. So on the calculator, 107.5 divided by 60. And we get not the nicest of decimals. It is as a fraction, but I'll write the decimal out. 1.7916, and it's a recurring 6 there. So that's our time in hours. Let's write that in there. And that is our upper bound, sorry, our lower bound. And that's what we want to divide by. So we're going to put that into the bottom of our fraction for our working out, although I am going to leave that number on the calculator. So 1.7916. And that's what we want to divide 275 by. So on my calculator, I'm just going to press 275 divided by the answer, using the answer button, pressing equals, and we have our answer here. And that's come out as 153.4883, and a lot more decimals. There is a recurring above the 4 there, but the important thing here is that that number is not above 160. So the answer here would be no, and that is backed up by our working, because we've just worked out that the fastest possible speed there is 153.488. Right, there we go, there is part A. Now part B brings some reasoning into this. It says here, if the track was measured as a 270 kilometres correct to the nearest 5, which is obviously more accurate than our previous one, how could this affect your decision in part A? Well, if it was measured to the nearest 5, that would mean that our upper bound would no longer be 275. Let's just write this here. So our upper bound now would only be 2.5 above. So it would be 272.5. Okay, just going 2.5 above 270. And that would be our upper bound. Now that's reducing our numerator there, or the number that we're dividing into. So in other words, we would have a smaller distance, but we would be dividing by the same time. So the speed would drop. Okay, if we have a smaller number there on the top, we're going to get a smaller speed. So in terms of this one, how could this affect your answer? Well, it could mean that the speed would drop. Okay, so our answer would change in that way. In regards to this one though, in terms of our actual answer here, it's not going to change it because we've not hit the 160 kilometers per mark anyway. It's 153, so even if we do reduce the speed there, it's still not actually going to affect our answer. But we got two answers here. It's not going to affect our decision because it's only ever going to reduce the speed. But in terms of our actual answer, it could drop the speed. So we just have to pay attention to the words here. It says, how could this affect your decision? Well, actually, it's not going to affect the decision at all because the speed is going to be reduced and it's not over 160 kilometers anyway. So we could just say either of those sort of phrases that we put together there. But I think the best answer we could give there is it's not going to affect our answer as it's going to result in a smaller speed. So there we go, there's that question. Let's have a look at another speed, distance, time question. This one's a little bit more tricky, but I'll let you make up your mind yourself. Let's have a look at that one now. Okay, so here we have our second to last question. It says here a high-speed train travels a distance of 487 kilometres in 3 hours. It says the distance is measured correct to the nearest kilometre and the time is measured correct to the nearest minute. It says here by considering bounds, work out the average speed in kilometres per minute of the train to a suitable degree of accuracy, and you must show all of your work in and give a reason for your answer. So obviously we've got something different in here anyway. We've got by considering bounds, which means we need to work out both the upper and the lower bound of our speed, and then we'll make a comparison and a final statement from that. So we'll have a look. Now, first of all, let's write our inequalities here, or our error intervals. So the distance, we've got 487, and that is correct to the nearest kilometre, so we can go 0.5 above and below. So 487.5 and 486.5 as our lower bound. So there's our distance sorted. The next one is the time, and we're looking at it in minutes. And obviously we've been given 3 hours there. So 3 hours in minutes is 180 minutes. And again, that's correct to the nearest minute, so we can go 0.5 above and below. So again, let's do that. We've got 180.5 minutes and 179.5 minutes for our lower bound. Okay, so looking at this then. Now we know that speed, again, just for like the first question, is distance over time. So again, we'll write down our formula. Speed is distance over time. And we're going to work out the upper bound of the speed and the lower bound of the speed. So again, we're going to need our calculators here because we've got some horrible calculations to do. But we are going to go for, first, let's go for the lower bound. So the lower bound is going to equal the biggest, or the biggest on the bottom and the smallest on the top. So we want our lower bound for the distance, and we'll divide it by the upper bound of the time. So if we actually go ahead and work that out, the lower bound of the distance, so our smallest distance there, is 486.5, and we're going to divide that by the upper bound of the time, which is 180.5, and that's going to give us our smallest possible answer, or our smallest possible speed. As well as that, we're going to work out the upper bound, which is going to be the biggest possible distance, divided by the lowest possible speed. And again, if we plug those numbers in, we're going to get the 487.5 as our distance, and our fastest possible time, which is 179.5. And again, let's work both these out. So for the first one there, 486.5 divided by 180.5, and that gives us an answer here. And let's write down all the digits, 2.695, and what have we got after that? 290, and a few more, 859. There we go, so there's our lower bound. Now if we work out the other one, so 487.5, I'm going to divide that by 179.5, and again, convert that into a decimal, and we have 2.715, 877 and 437. There we go. So we've got our two answers, our lower bound and our upper bound, and in order to get our final answer here, and this is where we're considering the two bounds, we can give our final answer. Now looking at these to 3 decimal places, let's just draw a little line in here. So to 3 decimal places, one rounds to 2.695 and the other rounds to 2.716. So that doesn't match. So we'll get rid of those and we'll try 2 decimal places. So to 2 decimal places, the top one there rounds to 2.70 and the bottom one rounds to 2.72. So again, we don't get a match. So let's go to 1 decimal place. And there we go, to one decimal place. The top one rounds to 2.7 and the bottom one also rounds to 2.7. So our final answer here is going to round to 2.7. So we'll say 2.7 kilometers per minute. And the reason there is that we've rounded it to one decimal place, or we could say two significant figures, either one. So I'm just going to write as my reason, one decimal place. Okay, obviously you could say two significant figures there as well, but there is my reason, and there is my answer, 2.7 kilometers per minute, and my reason there, one decimal place. So there we go, that is our second to last question. Now we're going to have a look at our final question, again using all of these methods, but again just a little bit trickier now for this final one. So let's have a look at that now. Okay, so moving on to our final question. We've got here, James is trying to find the density in grams per centimetre cubed of a block of wood. And the block of wood is in the shape of a cuboid. The length as 13.2 centimetres, correct to the nearest millimetre. The width as 16.0 centimetres, correct to the nearest millimetre. And the height as 21.7 centimetres, correct to the nearest millimetre. It says here that he measures the mass as 1,970 grams, correct to the nearest 5. And then again, we've got this statement here, by considering bounds, work out the density of the wood and give your answer to a suitable degree of accuracy. And again, you must show all your work and give a final reason. So again, we've got a different compound measure involved here. We've got density involved. But we're going to treat this in a very similar way to what we did with speed, distance, time. So we know that density is equal to mass divided by volume. So density equals mass over volume. So in order to work out the densities here, we need to get the mass and we need to get the volume. But we are obviously looking at considering bounds. So in order to consider bounds, we need the upper bound and the lower bound. And again, we're doing a division here. So to get the upper bound of the density, we're going to do the biggest divided by the smallest. And to get the lower bound of the density, we're going to do the smallest divided by the biggest. So in order to do that, easy enough with the mass, but the volume is going to take a little bit more working out in this question. So again, it is a cuboid, so it's easy enough to work out the volume. We obviously just multiply all the sides together, or find the area of the front face and multiply it by the depth, whichever way you prefer to look at working out the volume of a cuboid. But to start with, let's write our error interval for the mass, and I'm going to write it down below here because we've got quite a few numbers that are going to fill up this page. So if it's 1,970, and again, if that is correct to the nearest 5, we're going to go 2.5 above and below. So 1,972.5, and below that 1,967.5. So there's our inequality for the mass. Next, we need to find the volume. Now, rather than write down the inequalities for all of these, I'm just going to write down the inequality for one, just to avoid having too much written down here. But if that's correct to the nearest millimetre, that's going to be 13.15 for the lower bound of that length, obviously with 13.2 there, and that's going to be 13.25 for the upper bound of that length. That's going to be the same for all of those lengths there. But ultimately, we want to work out these volumes. So if we first work out the lower bound for the volume, okay, and let's just write this here, lower bound for the volume, we are going to multiply together all the smallest possible lengths. So that would be 13.15 multiplied by, and again, let's just highlight these. I'm just looking at all these numbers over here. So the lower bound for that 16.0 will be 15.95. 15.95, and then multiplying that by 21.65, that last length there. So that is going to give us the lower bound for our volume. And if we work that out, let's type it all in, 13.15 times 15.95 times 21.65, we get a final answer here for our lower bound of our volume of 4,540. And then lots of decimals here, 925 and 125. There we go. Let's highlight that so we don't lose it. So there's the lower bound of the volume. I need to do the same for the upper bound. So let's do the upper bound for the volume as well. And again, all we're going to do is the same process, but we'll use the upper bound numbers. So we're going to have 13.25. We're going to multiply that by 16.05 and multiply that by 21.75. And again, let's type that into the calculator, see what we get. So 13.25 times 16.05 times 21.75. and that gives us a different number here, obviously. So we've got 4,625, that's going to be 0.409, and then 375. There we go, and that's the upper bound for our volume. Now the rest of the steps now are easy enough. Obviously we just need to do the mass divided by the volume and take into account how we're going to do that to get an upper and a lower bound. So let's work this out down here. So the upper bound. So in order to work out the upper bound, we're going to want the biggest possible mass, which we know again from our inequality here. Let's highlight that, 1,972.5. We'll highlight the lower bound there so we don't lose that. So the biggest possible mass, 1,972.5. I'm going to divide that by the smallest possible volume. So the smallest possible volume there, we've already written it down, 4,540.925125, and there we go, let's type that in. So 1972.5 divided by 4540.925125. There we go, and that gives us a final answer here of 0.43 438 and 28506. They're probably not going to need that many decimals, but it's always best to write them all down. Right, so let's work out our lower bound. So for the lower bound, we're going to want the smallest possible mass, so 1967.5, and we're going to divide that by the biggest possible volume, and that upper volume there is 4,625.409375. There we go, and let's type that in. So 1967.5 divided by 4625.409375 equals, and there we go, we get 0.42 and then 536, and after that 77546. Perfect. So there we go, we have our upper bound and our lower bound for our density. Now all we need to do is do this by considering bounds element here. So if we have a look at these answers, and again let's go for 3 decimal places. So for 3 decimal places, which would be here and here, that would be 0.434 and 0.425. So again, there's no match there. So let's go back to 2 decimal places. And again, you could go more accurate, but if it doesn't match there, at least we know we don't need to go any more accurate. So let's have a look now. So we've got 0.43 on the top and 0.43 on the bottom. There we go. So they both round to 0.43, and that right there is to 2 decimal places. So if I get rid of this formula up here, and we can write our answer up here. So the final answer, we're going to have 0.43. The context of the question, it was asking us about density, and that was in grams per centimetre cubed. So 0.43 grams per centimetre cubed, and again that is, our reason was 2 decimal places. And there we go, and there's our final answer. So let's highlight that off, final answer, last question, and that is the end of our questions. Hopefully you found that really nice and helpful. Again, as I said, don't forget to check out the video on bounds, which I'll obviously link in the description, and also the video on error intervals. But hopefully you found that useful and helpful, a nice little selection of questions for you there. And until the next one, please do like, comment and subscribe. Please don't forget to share the videos with anybody else that you might find this useful. But otherwise, I'll see you on the next one.